Alright, section 5.2 kind of follows up on section 5.1. Remember, going from section 5.0, we were kind of changing gears because 5.0 was on scatter plots and their lines of best fit. But then we sort of changed over to systems of equations. But in 5.1, here I'm literally reading this right now. In 5.1, we saw that if we wanted to discuss a linear system and what the situation is with the solutions, we would need to what? Like what's the method we know of at this point for solving a system of two linear equations? And basically, what did we do in section 5.1? We graphed both lines, remember? So that was the first way we sort of looked at for figuring out what the solution would be for like a system of two equations at the same time. We would graph both lines and see if they shared any solutions in common, shared any points in common. And most of the time I'd say they do intersect at one point, which would be your one answer. But sometimes the two lines are parallel of each other and there's not going to be a solution when the two lines are parallel. But then sometimes it turns out that your two equations make the exact same line and the lines are over top of each other. And in those situations, you have like an infinite number of solutions for the system. But anyway, that was the method we used. But can you think of any drawbacks or disadvantages to this method? Like, where would the method of like graphing both of the lines in order to see where they cross, where could that go wrong? And again, I'm not talking about the two lines being parallel and never intersecting, and I'm not talking about it being the exact same line over top of each other. That's not what I'm talking. I'm talking about like a real problem with graphing both lines. And if you were in class when we did this section, this lesson, we probably did an activity that sort of flushed this out and showed you a scenario where the graphing method is not quite good enough. And as a matter of fact, give me a second and I'll show you. Should I call that up on my computer? Yeah, might as well show you. This is what we did in class, in case you missed it. Let's say I wanted you to solve this system by graphing. So just want to like make sure that we're seeing everything. So here's the system, okay? But what kind of color could I use here? Now, this equation is good to go. Okay, in fact, it's already, so maybe I'll just use that color, right? So this equation, I'll just circle this one again. I clicked on red, I swear. So anyway, without any further disruptions, well, maybe one more. Without any further disruptions, so this equation was good to go, but this equation needed to be changed to this. So at the end of the day, the two lines you're graphing come from, this equation and this equation. So when if you were to graph these two lines, here's what happens. Okay? You graph these two lines, and then you look at it and go, all right, so where do these two lines intersect? And, they intersect right there, but where is that? Like, where is there? What are the coordinates of that point? And I'm sure you could take a crack at it, but I guarantee you'd be wrong. Guarantee. Because the coordinates of where those two lines cross turn out to be x equals 55/38, comma 43/38. So basically, this is where they cross, which is approximately 1.447, comma 1.132. So, basically that little sidebar I just did, that's one of the drawbacks. And you know what? It's probably better. Yeah, it's inaccurate and whatever, but maybe we should kind of be a little more specific. The lines don't cross at a nice point, right? Think about it. If you graph two lines, they don't have to cross somewhere nice. And again, like by nice point, both coordinates are nice integers, So that's one thing that could go wrong. But you know what? Can you think of another thing that could go wrong where you try graphing both lines and you just can't get an answer from your graphs? Well, here's the other one. What if the lines won't cross until, how can I better write this? The lines won't cross in bounds, on your paper. No, I don't know. I'm sure there's a better way to write that. I just can't think of it right now. Basically, what I'm saying is, even though here I go about to explain it. What if the lines are supposed to cross like really far away from the origin? Maybe I'll write that down. Really far away from the origin, Like, for example, what if your two lines are going to cross at like 130, comma, negative 257? How are you going to know that? Like, just on your little piece of paper, on your little graph, you know what I mean? So those are just two things that could go wrong, like really wrong, like fundamentally wrong with the actual method, Nothing you're doing wrong. It's just the lines don't cross at a nice point, or the lines won't cross until, you're really, really, really far away from the origin at like really big numbers. So basically, gosh, how long has this video gone so far? And we're just now getting to this. So there's got to be a better way. What an intro that was. What a build-up. Behold the substitution method. Okay, so we got to get a little a little fancier. We got to get a little more reliable. So using a graph won't always be reliable, even though it. I mean, I don't want to. Basically, the graph. I don't want to make the graphing method sound so bad, when, in all likelihood, like the graphing method will probably be just fine. But hey, there's better methods out there where we just go with the equations, where we go with a more algebraic method, which is going to be more reliable no matter what kind of answer you're supposed to be getting. So here we go. Step 0 of the substitution method, that's right, step 0 is going to be make sure one of the equations is solved for a variable. Sorry, that got cut off a little bit off the screen, but that obviously says variable. So make sure one of the equations is solved for a variable. What that means is, before you can even think about doing this substitution method, one of the equations has to say x equals, and then the rest of the equation, or y equals whatever, or whatever equals x, or whatever. Basically, you need to have an x all by itself on one side of the equation, or you have to have a y all by itself on one side of the equation. Okay? Which we have here already. Because look at the second equation. It says y equals 2x minus 7. So we're good to go. Step 0 is taken care of, okay? So step 1 after that, if you have that, step 1 is going to be substitute that equation into the other one. So here's what's going on with that. This equation is essentially saying that y equals this. This entire 2x minus 7 is what y equals. Well, in the other equation, we have, you guessed it, a y. Okay? Okay? And if the other equation is basically like spilling the beans about, hey, this y up here, it's actually equal to 2x minus 7. So you can basically substitute this entire 2x minus 7 in for the y in the other equation, because that's what y equals. So guess what? The first equation will become 4x plus 3 times y. But we're going to substitute 2x minus 7 in for that y. So the 3 is still here, like we still there. It's only in for the y we're going to throw that 2x minus 7 in for. And then equals what? So 4x plus 3y equals 4. So we've basically just like updated, updated my first equation, except instead of writing y, I just wrote what y equals, 2x minus 7. And that's step 1. That's the money step. Now, why do you think that was a good thing to do? In other words, what do you think step 2 is going to be? What's the next step? Where do we go from here? Why was that a brilliant maneuver? Well, because 4x plus 3 times 2x minus 7, we can solve this now. You know why? Because now this equation only has one variable in it, the x variable. And therefore we can solve it. We can solve for x. The first thing we're going to do to solve for x is clear the bubble. This is stuff you learned a long time ago. So when we distribute the 3, we get 6x minus 21 equals 4. The next step, which you should be comfortable with at this point in time, is if you see two like terms that are already on the same side together, you combine them. 4x plus 6x is 10x. And now we can continue to get x by itself by adding 21 to both sides. I'm not going to write down every little thing because I'm running out of room on my paper, but I'm going to add 21 to both sides and get 10x equals 25. Okay? And then the next thing you should probably write down is that we are going to now divide both sides by 10 to finish getting x all alone. And so 25 divided by 10 is 2.5 or 2.5. And so that's what x equals. Okay? And that's that step 2. So what's step 3? I mean, why aren't we done? Like, we know that x equals 2.5. Why is there a step 3? Well, if we're solving a system of two equations that both have an x and a y, you can't just solve for x to solve this system. You also need to know what y equals. Well, it's actually not going to be that complicated because we can actually use this first answer to our advantage. Now that we know that x equals 2.5, we can plug that in for either one of these two equations. But you know what? It's pretty obvious to me that the second equation is probably going to be the better, easier option. So now y equals 2x minus 7. Well, now I know that x is actually 2.5. So it's 2 times 2.5 minus 7. So that's what this equation has become now that I know what to plug in for x. And so 2 times 2.5 is 5. Minus 7 is going to equal negative 2. So the final answer is 2.5 comma negative 2, because x was that, y was that. And that's how the substitution method works, people. As long as you know what x equals or what y equals from the start, you can substitute that in for that letter in the other equation, which will create an equation that you can now actually solve. And so you get the first answer, whether it's x or it could be y, and then you use that answer to get the other answer for the other variable. So here's the next example, and I'd say feel free to try this on your own, but I don't know if I'm going to recommend you do that, because there's actually a plot twist to this problem, and the plot twist is that step 0 is not accomplished. Step 0 says that we need to have one of the equations solve for x or solve for y. We do not have that here. So what you have to do is make that happen. You have to take one of the equations, your choice, and solve it for one of the variables, x or y, your choice. But there's normally one or two options that are like the best option or the best, easiest options. Now, I'm looking at the second equation, and I'm thinking solving this equation for x is going to be very simple. But you know what? I could also solve it for y very simply. Compare that to the first equation. Imagine trying to solve the first equation for x. No thank you. That's like at least two steps. And there might be some ugly fractions involved because I'm going to have to divide by 2 to get x by itself. No thank you. I mean, I could if I had to, but no thanks. Also, what if I decided to solve for this y? Once again, you're going to end up at some point dividing both sides by -3, probably creating a nasty fraction. it would work, but no thanks. I'm going to pick either this x or this y. It's not going to be that big of a deal. And you know what? I'm going to pick x. So how do I get x by itself? I just have to subtract this out of there. And so I'll have x equals, can we do negative 12 minus y? Nope. And so the other side will just say negative 12 minus y. So now I know that x equals this. That's what x is. I just dropped my pen. Hope it's not broken. So that's what x is. Now, oh my gosh, let me take a breath because I want to tell you something important. Because here's what's going to happen next, right? Now I have to take this negative 12 minus y and plug it in for x. But I don't want you to make the following mistake. Watch the pen here. If you plug negative 12 minus y in for this x, the problem's going to like blow up in your face a little bit. Okay? Remember, this equation, okay? This equation is where this came from in the first place. Don't plug this back into the same equation that this came from. That's not going to get you anywhere. What I'm saying here is you have to take this negative 12 minus y and plug it into the other equation. Plug it in for the x in the other equation. And so what you're going to get is 2. So it's almost like I could draw an arrow. That wasn't a great arrow. My shadow was in the way. That's better. So my first equation becomes 2x, but x is that. So I'm going to do 2, and then I'm going to put negative 12, you idiot, negative 12 minus y in parentheses. So there's my 2x. 2x minus 3y equals 6. Okay, now I have my super equation, but hey, I can solve this though. This equation only has a y in it, and so I can solve. First I clear the bubble. Negative 24 minus 2y, that's the distributive property. Bring down the rest. I see like terms that are already on the same side as each other. And so that makes minus 5y equals 6. Trying to fast track this because you've done this 1,000 times. You should know what you're doing at this point on. Well, I hope I do. Negative 5y equals 30. And so y equals negative 6, I do declare. So that's like half my answer, because remember, I also need to find x. Well, that's going to be pretty easy as long as I know what y is, okay? So here I go. I can plug negative 6 in for this y, or this y. It's your pick. I'm just gonna, not totally randomly, it's like I am picking this on purpose, but I would pick this one or this one. I'm gonna go with this one, okay? So x, and I'll even like rewrite it over here just to make it crystal clear. So now I know that y is negative 6, so x minus 6 equals negative 12, and so when I solve for x, okay, so x also equals negative 6, so my final answer is negative 6 comma negative 6. So this example was just like this example. I mean, I know here we got x and then y, and here we did it the reverse, you know, like we got y and then x. Okay, so they're different in that way. But the bigger difference is that this system was already perfectly set up for the substitution method because we knew that y equaled all of that. this example, we needed to take one of the equations and solve for something, and I chose here to solve for x, and we had to do this before we could even think about doing the substitution method. Okay? Here's the next example that we're going to do, and if you want to try this on your own, go for it. If you want to pause the video and try this on your own, go for it. So here I go in 5, 4, 3, 2, 1. This is not perfectly set up for substitution. So even though I could theoretically solve for this x, no thank you. I could solve for this y, but no thank you because of all the dividing I'd have to do and potential nasty fractions. Okay, let's get to the point. I'm going to solve for this y. I think that's going to be pretty clean and my best choice. So I'll even rewrite the equation over here. And even though you could just add y to the other side, and that would actually be the quickest way, I'm going to go ahead and do it this way. What if I were to subtract this 3x term out of there? I would end up with negative y. Yep, still a negative y. And the other side would be negative 3x. Now I'd have to, in a way, like here's one way to approach it, divide both sides by negative 1 in order to know that y equals positive 3x. Okay. So that's what y equals. Now again, you don't want to plug this back in to the equation it came from. Plug it into the other equation. So if y equals that, then I can replace this y 3 times. So what does y equal? 3x. So yes, I have 3 times 3x, okay? Remember, we're plugging it in for the y, not the whole term, just the y equals 3x. So yes, I have 3 and then 3x. So that's going to get me, okay, my board, I don't like when my board acts funny. So this becomes, what's 3 times 3x? 9x. These combine together, like you should know happens next. And then that leads very quickly to when we divide both sides by 13, we get x equals 2. So now we know that x equals 2. So now we can plug that in for an x somewhere so I can solve for y. Why not just do it here? Y equals 3 times, what was x again? 2. So y equals 6. And now I have the full answer of 2, because remember, it always goes x, comma, y. So make sure you put x, comma, y for your final answer. Now, I might as well say this right here and now. You could easily double check that this answer is correct. How might you do that? How could you possibly double check that this is correct? Remember, this is the solution to the system of equations. So what that means is you could take the 2, plug it back in for x, take the 6, plug it back in for y, and see if it actually solves both equations. So here we go. 3 times 2 is 6, minus 6 is 0. Okay, so check. 4 times 2 is 8. 3 times 6 is 18. 8 plus 18. Check. So check. Okay, now I'm going to stop the video here, purposefully to break up section 5.2 into two different videos. This first video was the substitution method. The next video, the other half of 5.2, is going to cover the elimination method. So just find the other half video on my channel to finish section 5.2.